first speaker is Tomo, who's going to tell us about some cool new JWST results.
Thank you very much. Hello everyone. Today I'm going to introduce my students' work, these 3 papers or 4 papers, to you. And before starting, I want to thank all my collaborators at NTHU and NTHU. So let's get started. So I want to start with a question: what is JWST? Then everybody has different answers to you. But my answer to this is JWST is 10 times larger Akari Space Infrared Telescope. I hope I can convince you in this talk. So let's start with a little bit of history. So I have been working with the Akari Space Infrared Telescope for the last 10 years. Akari is a 65 centimeters space infrared telescope, as you see in the background of the picture. And one of the good features, unique feature of Akari is its mid-infrared filters. If you recall, the white or spitzer shown here has gaps in wavelengths in mid-infrared. However, Akari has a continuous line by mid-infrared filters, so whatever your feature is going to read, whatever redshift, one of the filters can capture that directly. So that was a unique feature of Akari. By taking advantage of this filter, we've been doing a science, for example, cosmic star motion history model plot using Akari Space Infrared Telescope, so as shown here. So that's good, but our work is limited to sort of Euler's at spreadsheet 1 or 1.5-ish because Akari was only 65 centimeter telescope, it's not so sensitive. And next, we are looking forward to Spica next infrared telescope, space telescope, but it was cancelled, unfortunately. And then at that time, here came JWST, 6.5 meter infrared telescope. And then the reason why I say JWST is 10 times larger Akari is if you compare the mid-infrared filters, it's very similar. So the bottom one are Akari's mid-infrared filters, and then top one is JWST's mid-infrared filters. As you can see, JWST filters also nicely covering the mid-infrared wavelengths with 9 filters. So that's very advantageous for us. So whatever the codes or techniques we developed for Akari, we can directly use it for JWST and write papers. And JWST has a very generous data policy. In addition to early release observations, a lot of large surveys data immediately public, so there are plenty of science can be done with this survey, the JWST survey. However, at a university, we only have young students. There are interesting, questions like Tomo, how do I open Fritz files with Excel? So what can we do? And then the idea we came up is we do galaxy number count. Number count is very simple, right? It's how many galaxies are there as a function of flux. It's very simple, but fundamental statistics, but still important, I can show you later. So that's something I tried with my students. On data, we use the Stefan's quintet area and CS data in the early release observations. So one of my students produced 7, 10, 15 micron mid-infrared number counts from JWST, in this case using Stefan's quintet data. Okay, he's not measuring the Stefan's quintet, but the background galaxies later ones. And let's zoom into one of the plot. So this is 15 micron luminosity function he created. Then as you can see, these bright ones are from Akari and Spitzer here. Mini-Jansky sources are Akari and Spitzer, but with JWST data, we go to micro-Jansky, almost 2 orders fainter. You see these 2 orders from here to here. These are all JWST, and this is the power of the 6.5 meter telescope. And then luckily, this student, Jimmy, worked hard. So this paper was submitted in July, and then also the JWST data was released in July, right? And the paper was already accepted in September, and this is, I think, one of the first JWST paper from Taiwan. The another student did the same number counts in a Sears field, is another field, where there are more millimeter bands that are available, say 7 to 21 micron. And then this paper is also accepted. Okay, so far so good. But you might be thinking, these are just number counts. Anyone can count it. You're just counting galaxies. What's interesting? There's nothing interesting. That's true. It's boring. But what's important is how do we derive physics from here, such as cosmic star formation history. And usually when you have data, how to derive cosmic star formation history is you do this, right? Photology and acid fitting, luminosity function, integration, and cosmic star formation history. But this is too difficult for students. So the approach is okay. So then we took a model-based approach. So we use a model to fit the number count. And then this is how, let me explain the model. So this is how we did the model. So at redshift 0, we know the measured luminosity function, we do infrared luminosity function, the measure. And we take the shape, and then parameterize its evolution like this. Okay, using these 4 parameters. And then these 4 parameters describe the luminosity and density evolutions. And then we do that for 5 populations of galaxies, such as type 1 AGN, composite, starburst, star formation galaxies. And then, so 4 parameters for 5 populations, so we have 20 parameters. And then, once you determine these 20 parameters, you know everything. So what do you mean by that is like this. So once you determine these 20 parameters, you know the evolution of the luminosity function. So here, if you decide one set, then your luminosity function evolves from like this, 0 to 1, and then even high redshift, like this, for 5 different populations of galaxies. And once you know the luminosity function, you know exactly how they contribute to the number count, right? Because you know redshift luminosity, so you know the number. So you can describe it in terms of the number counts like this. In this case, it's 15 micron number counts. And then you compare this, you fit this with observational data. That's what we do as a model-based approach. So let's do the fitting. So the red points here are the JWST data number counts my students did. And then we're going to fit that model, the red one, to this data. So what we're doing is something like this. So as we change the parameter, you know, its shape changes, right? And we fit it to the JWST data. And here is a Madao probe 2. And as you can see, if you change the number count, Madao probe is also changing, right, in the bottom. So this is how we estimate cosmic star formation history from number counts. Okay, so let's do that. And actually, I showed this already. The red lines are the best fit lines for the number count. Okay, so now from the best fit, we know the 20 parameters, right? So then we know the evolution of luminosity functions. So we integrate that, then we get the cosmic star formation history like this. Okay, so the red one here is the Madao probe, the cosmic star formation history from JWST. This is infrared star formation history. And then, okay, you might be thinking, oh, you just agrees with previous work. But here's a important point. This is the first mini-infrared cosmic star formation history from JWST. And what's important is we are using micro-Jansky sources, 100 times better than the previous work. So all these previous work, although it agrees on this plot, based on previous work, based on milli-Jansky sources, and we are using 100 times fainter sources to create this. And then previously, those faint ends of the luminosity function, they are just extrapolating, you know, assumption, right? We're using the real data, so that's the fundamental difference. Okay, and then I'm good. And okay, I said data-driven approach, like regular approach to photology acid fitting, is too difficult for students, but then later students actually were able to do it. This good student Jimmy actually did it. So he did acid fitting here. So here, midi-infrared is of course JWST data, and this is CS field. So in optical and there's all kinds of data using Hubble. So he did the acid fitting, including photology. He measured photology, and then now you know that in luminosity and photology, right? And then so he created the luminosity functions, correcting the volume using Bmax method. He created luminosity functions. So this is JWST medium infrared luminosity function. And again, amazingly, these dotted lines, these ones, are previous work from Akare and Spitzer. And as you can see, those previous work is just looking at lugs and U-lugs and maybe, okay, 10 to the 10th luminosity, right? But JWST data is going all the way to here. So these are JWST data. And then now, not just U-lug and lugs, it's amazing. We are going to 10 to the 9th, 10 to the 8th, sometimes 10 to the 7th solar luminosity. So we are looking at regular star-forming galaxies at these high redshift. That's the power of the JWST. And then now Jimmy, my student, integrated this luminosity function, and then you get the matter plot, right? That's here. Okay, so this black curve here is the cosmic star formation history from JWST. And then here, important point is, well, again, this is the first mid-infrared cosmic star formation history from JWST, so it's mid-infrared, so it's mostly extinction-free. And also, this is the first time mid-infrared luminosity function is going to redshift 4. That's the first time. Then also, again, we are using the micro-Jansky sources 100 times fainter than previous Akari or Spitzer. So now we are measuring the real sources instead of extrapolating luminosity function to guess how many sources are out there. So that's the important point of this plot. Okay, let's summarize. So I talked about JWST number counts, then JWST cosmic star formation history. Then I hope I was able to show that even undergrad students can do an interesting science with JWST. And then, fortunately, they all came to grad school, so that's so far so good. Thank you very much. Thank you, everyone. Thank you, organizers. I stop here. Thank you.
All right, do we have any questions for Koto-san? Okay. While we are thinking, because again, we have plenty of time since the next speaker is missing, so come up with some questions. I just had a couple quick clarifying questions that I probably just missed. When you talked about this sort of analytical fit with the 5 different populations, I might have just missed it, but do you constrain the relative proportion of those 5 populations' contributions?
Yes.
Yes, okay, that comes out. Nice. Do you have what those proportions are on hand in your presentation, like a backup slide, or?
Not here. Yeah,
Okay.
we made that plot.
Okay.
Not here. Sorry.
It's okay.
We don't have it here. Yeah.
Okay.
Well, it's generally, it was interesting. It might agree with the general expectation, like if you go high Z, high luminosity, agent fraction goes down.
Okay.
Things like that, yeah.
Nice.
It made sense. So.
Hello, thanks for your very nice talk. It's very funny that the students can do such a very interesting science project. Actually, my first science project also number counts, but it's not in the not in the infrared, but in the some millimeter band. When we do number counts in some millimeter band, we also say that it can constrain the models. But the problem is that when you do number counts, because you are actually looking at the projected universe. So all your models actually also have a kind of their free parameters have lots of degeneracy between each other. So for your modeling, have you also checked that degeneracies between your 20 free parameters?
That's a good question. Well, actually, Sonjin, this guy is the who performed this model fitting, and he's running the MC, but he hasn't finished it yet, so I don't have that plot yet. But you're right, it's very important to check this degeneracy.
In the meantime, when doing number counts, you need to actually separate the sources. For example, in those images, how do you handle the kind of close merger, for example, to separate them and measure their flux in a reliable way?
Well, I think, yeah, that's a good point, but that's all, I think, relatively easier with JWST because the resolution is good. So we don't have too much problem of the overlapping sources.
Okay, thank you.
Do we have any questions from anyone online? Use your hand raise feature in Zoom. Okay, well, we're still waiting. I have another minor question for you. In one of the earlier plots, when you showed the results for the Stevens quintet field,
Right.
I noticed that there were some quite different sizes of uncertainties in adjacent bins. Is that just because of the numbers of galaxies and it's just a small field and that went away with bigger fields, or there's something else going on there that I'm not sure of?
You're talking about these?
Yeah, so like there would be adjacent bins and some of them, the error bars are like half the size of the others. Is that just because it's a small field and they have a limited number of sources?
Yeah.
Okay.
So in the end, when we do the fitting, we combine all the fields in this and then spheres.
Mhm.
So the field is a little bit larger than this here.
Okay. Any other questions?
Sorry, I have another question. I think after the James Webb launched, when people were checking the pipeline, they found that there's a problem with their pipeline that can give a wrong photometry for the measurements. Whether that issue affects your measurements here?
We did the photometry by ourselves.
I mean, it's the problem of their pipeline.
Okay. I don't know what specific problem you're talking about, so maybe I talk to you later.
And it's because they don't fully calibrate the instrument. They use some extrapolation. I also forget the detail, but it means that in several bands that the photometry is not accurate. But they released their updated version of the pipeline that should be have this problem correctly.
Okay, well, these works are based on, obviously, all the pipeline. But
because you are kind of the first paper
Right.
using the James Webb data. So yeah, I thought that maybe you have aware of this problem.
Okay. I'll check. Thank you.
Also, very nice talk. So it's very impressive to see that your cosmic assumption history agrees with the other measurements. Yeah, very nicely, actually, too good to me. And so, is that because you actually fine-tuned the parameters to match the previous measurements, or is it just by coincidence?
Okay. So there are two ways to answer this. So previous one, this model-based approach, this one, it's actually this evolution. It's the model shape, model function shape, is actually chosen to sort of reproduce these kind of, like a peak and a tail. So that's the functional shape. So it can only change within this kind of shape. It can like change the slope and peak, but not like in a zigzag way or something like that. So in that sense, since your point is correct, that we sort of limit the functional shape. That's because in this case we only have a number count, so we have to do more constraints from the modeling side. But this one is different. So this one is just we created a luminosity function and then integrated. So this is free from that kind of functional shape. So that's why we have only 4 points.
Mm-hmm. Thank you.
I can ask another question. So you've shown very beautifully that all of your results, at least in the duration of this talk seem to agree very nicely with what we expected. Were there any results that came out of this work that you were a little bit surprised by? Anything unusual, or are we good on our ideas of galaxy evolution?
Anything surprising?
Yeah.
Well, I didn't show the AGN part of this. So actually, we have the AGN, but we subtracted AGN from this. So we have AGN part, so AGN acquisition history. But then that one came out a little bit higher than previous work. So we're trying to figure out, is that true, or why is that? That's something surprising or remaining task for us to do.
All right, very nice. Okay, we still have like a good 9 minutes until when our next talk is supposed to start. So we can ask more questions, or we can take an email break, your choice.
I can give another talk, but that wouldn't be appropriate. Another student worked on found the Brown star from this data, so I can talk about, but probably that's not.
I mean, like, if you want to highlight it quickly, I mean, what else are they going to do? So.
Thank you very much. I think she's going to be happy because I showed the slides and her work was not included, so she was not happy. So, brown dwarf it's something between stars and the planets, so that's important as a transition object, right? And then JWST filters are also very good for finding these because, or in this case, it's near count, not mid infrared, but in the near infrared. And then you see many filters in near infrared, right? This is very good for brown dwarf stars because, as I said before, previously, Spitzer, they had like 4 filters here, right? And JWST had so many in near infrared. And then this 2.7 micron filter is right at the water absorption here, where the star's temperature goes lower, then there's more and more water absorption here, right? And that's at 2.7 microns, so this is perfect to find brown dwarf stars. And then so my student in Poya look for brown dwarf stars, and then if they have a deep absorption at 2.7 micron, they should, be very in this area, green area. And these green ones are models, but the red one is the data, and she found one data here. And then that is this one, and then as you see, this the bottom point, 2.7 micron, is very deep, right? You see, so these are data point, and then here it's a very deep dip, and this is very difficult to create with galaxy, right? You have never seen this kind of galaxy doing this, right? So this is most likely be a brown dwarf star. Or she did perform the acid fitting, and then of course the best fit is a brown dwarf star with 1300 Kelvin temperature. With this kind of parameter would be the other parameter. And then this is again it's JWST, so this is 4 micron is 27 magnitude, and then that makes this to 5 kiloparsec away. That's by far the farthest brown dwarf star ever found. Then this 5 kiloparsec, right? So it's not even a galactic disk anymore. It's like thick disk or even halo or something like that. Then type is, if we compare with previous data spectra, then type is T-dwarf type if it fits well. So the data, then this background is previously non-T-dwarf, and it fits well, right? If I show the post-step images here, it's not extended. We check with the source extractor, it's not extended, so it's consistent with your star. And what about the number density? So we searched all the early release observation data, so shears, Stefan's quintet, and the glass field, so this is 16 arcs per minute. And then expected number density here is something like 0.15. And then we found 1, so I think that's not impossible. We have to be very lucky to find 1 when we expect 0.15, but I think it's fine. I think we're just lucky. Or maybe in fixed disk, the number density of T-dwarf stars are higher, that's also not impossible. So that's another nice result by my student, and then her paper is just accepted. Thank you very much. Okay. She'll be very happy.
Do you have any questions about T-Doors?
Another very interesting talk, Goto-san.
Thank you.
Yeah, very nice. Yeah, actually, one question is you mentioned that the age of this expected brown dwarf is something like 15 a year. Am I correct?
Okay, sorry.
How reliable this is?
Sorry, sorry. This is old results. This is too young, and then we redone the fitting, and then we found something something a little bit older. So I didn't update the number.
Oh, really? Because this might mean that there must be some ongoing, well, not only on the recent start, some much activity.
Right.
But this is not what it means. Yeah. Because I'm really wondering if there any kind of sound emission out of far out of the 60s, and it must be another very interesting.
Thank you. That's a very good point. Thank you.
Okay, I think that's probably good.
Thank
Thank you again.
Thank you very much.